PhD scholar. Okay. Hello, everyone. I am Preetham. I am a PhD scholar of Indian. I am a PhD scholar from Indian Institute of Science. Today, I'll be conducting the TS session for the based on like whatever you were taught in the recent week. I mean, week 8. So mainly, I'll be discussing about the PCS superconductor, Josephson junction, the two-level system, and all that. I mean, whatever you guys were taught by the professor, and I will try to cover some sample. I'll try to cover some concepts today, so which will help you to solve the assignment questions. So as you know, I cannot directly discuss the design assignment questions. So I have prepared a few slides. So basically, if you go through that, you will get a understanding of how to solve that kind of problem. So it's basically a concept. It will be basically a concept clearing session. So whatever was taught by the professor, I will basically I have prepared few slides based on the like from where exactly the questions from in your mind from your mind comes out. So based on that, I have prepared few slides. So I'm sharing my screen. I hope it is visible. One second, just let me check whether my voice. Yeah, it should be clear. I think, yeah. So I'm sharing my screen first. So as you know, a two-level system basically it's a quantum system, right? So it's a combined system. So that can exist in the any kind of quantum superposition of two independent quantum state, right? All these quantum states are basically defined by the particular wave function. So each state corresponds to one wave function. So that wave function will define that quantum state. So the Hilbert space, as you know, basically it's describing in such a way that it's in the two dimensional. So we discuss the certain general properties of the two level system, and we will introduce the application how in the real life we'll get the two level system. So such yeah, exactly. So it's and how what are the mathematical model and how the wave function look like. Basically, we'll be discussing about that in today's session. So these are the general concepts. So two level systems are the simplest quantum system because the dynamics associated with it is it's trivial. So there are no other states in the system can exist. Okay, so it's very important for many cases. We can use some approximation to simplify the problem and change it into the two level system. So we can basically simplify the complicated problem and convert into a two level system, which will be a very easier way to handle the thing, right? So suppose for an example, for a physical system we have two states, right, whose energies are close together and very different from all those other states will be existing. So we are taking two states whose energy very close, but we may have some other states that will be present in the system. So this state ka energy will be different from all other energy states that we have in the system. So first assume we want to evaluate the effect of an external potential. So suppose if we put some external potential, so how the system will act. So for the time being, we are not considering the internal interaction between the state. Suppose we have a system full of electrons. Okay, we have some electrons in the state occupied by occupied a state will be occupied by the Fermi distribution function, right? So let's say that is given. So we are not considering any electron interaction in the system. Instead of that, if we put some external perturbation on the system, so how the system will behave after the application of the external potential or perturbation, whatever. So that is the point of that is the matter of the discussion. Okay. So suppose we all know about the first order perturbation, second order perturbation. So suppose the perturbation what we are applying on the system is very weak. I mean the intensity of the perturbation is very weak. Then what we can do, basically the effect on the two states can be easily calculated by ignoring the all other energy levels of the system. So this is called the first order approximation, right? So all the calculations can be performed in a two-dimensional space considering this thing as a two-level system. So this is the approximation that we're gonna use. Okay, so this is the hypothesis. So if suppose we have considered the two-level system, so we have two energy eigenstates, let's say phi a and phi b, with the energy ea and eb respectively. Okay, now we have the Hamiltonian, let's say h naught. So by as you know, by the normal convention, so if you apply the Hamiltonian on the state, it will give us a eigenvalue, right? So ea is the eigenvalue associated with the phi, and phi eb is the eigenvalue associated with the phi b. So these are the basis. So you are considering this to be orthonormal. So according to the criteria, so this bracket of the phi I phi j will give you the Kronecker delta, right? So that's why they are orthonormal. So how we can write in this write the Hamiltonian in a matrix form? So that will be purely diagonal, right? As this the basis of the this matrix are basically orthonormal to each other. That's why we can write in this way. Now we consider, suppose we are coupling with some external perturbation, let's say V, and that has a matrix form of 0 VAB VVA 0. So now we'll add the perturbation to the the original Hamiltonian H naught, and we are getting a modified Hamiltonian H in the system. Okay. So once we have considered this, we're having a total Hamiltonian which will look like this. Let me turn on the pointer once. I hope it's visible now. So this is the total Hamiltonian. And suppose for the time being, you assume this V is basically time independent. Okay. So because this V should be, I mean, this V should be Hermitian. Okay. So what is the criteria? VAB star will be equals to VBA. Then we can write the Hamiltonian in this way. EA V e to the power minus E5 and so on. So in this way, basically simply we can write the Hamiltonian. Okay. So if we are asked to find out the eigenstate associated with the Hamiltonian, I mean for this Hamiltonian, what are the eigenstate? Then to do that, we need to diagonalize the Hamiltonian. As you know, so simply we have to do the determinant of h minus lambda I. But lambda is a constant parameter, I is the unit matrix, 2 by 2 unit matrix, and h is the Hamiltonian. Okay. Basically, this is called the diagonalization. I mean, if you are asked to find out the eigenvalue, this is the only way you can find out the eigenvalue corresponding to the eigenstates. Okay. So if you simplify this and calculate this thing, you will end up with having energy eigenstate corresponding to the two level system, and exactly the two energy states, right? Because it's a two level system. So for simplicity, I'm here defining a parameter called, let's say, E is equals to what is half of EA plus EB, and a delta is defined as EA minus EB by 2. Now we get separate eigenvalue, right? One is E plus, another is E minus in terms of the parameter E, delta, and the external perturbation V. So as you can see, this is just like, suppose we have a energy, let's say E. So it's above delta square root over delta square plus V square, and this energy lying below to that E. I mean, below root over delta square plus V square this amount. Okay. It's like a symmetric about that energy value E. Okay, this is just for the simplification or is in a way to easy to understand the problem. So these are the eigenvectors associated with this energy eigenvalue. Okay, that you can easily calculate. So here theta is defined in such a way that tan theta will be equals to V over delta. So if we show how this will look, I mean, in a graphical representation. So this is the graph for the energy eigenvalue. As I already told you, E plus will be lying here, E minus will be lying here. So this is the graphical representation. We can see from the graph that when there are no coupling, the levels across, I mean, that when there is no coupling, the levels cross at the origin, right? That you can see. No couplings means V equals to 0 that time. Exactly. Under the effect of non-diagonal coupling V, the two level becomes part of high parabola. So then it will be high parabola. Okay. As from the equation, it's very clear. So this is very important. I mean, under the effect of the external perturbation, how the system is going to behave. Though we are approximating, we are not considering any kind of electron interaction, any kind of systematic interaction, but under the application of the external uh, potential, like which can be considered as a non-diagonal coupling, let's say V. Why we are calling it as a non-diagonal? Because you can see whatever the form of the V is, it's actually non-diagonal. So we have a non-diagonal element VAB and VBA. That is why it's called a non-diagonal coupling. Once we consider this, the two-level system, two levels becomes a part of the hyper, right? So now here are the two situations we have to deal with. So let's say we have a strong coupling. What do we mean by the strong coupling? The magnitude of the V will be greater than that mod of the delta. Okay. Once we consider this, we will have something like this. Then we can define the energy eigenstate accordingly. Okay. So this you can see psi plus minus, I mean upper state and lower state. If you define in this way, then we are having this equals to 1 over root 2 times uh, phi a plus minus phi b. So this eigenstates are symmetric and basically it's a combination of the symmetric and antisymmetric, right? So suppose we have a weak coupling, what we'll have? We'll simply, I mean, in that limit, when mod of V less than the mod of delta. This, okay. I mean, delta is very small. Means what do we actually mean? Delta is very small. Delta is very small means the EA, the energy value corresponding to A will be very much similar to corresponding energy value of B. So EA and EB will be almost close, right? That's what it means. When delta is very large, that means there is a sufficient amount of difference between the energy of the two states. But when we are having a very small delta, so it basically imply that there is a very tiny amount of difference between these two energy state. The energy value, difference in the energy value is very small. Okay. So then we are having a eigenstate which will be for the psi plus will be phi a and psi minus will be phi b. This is like completely independent. But when we are having a coupling, basically it's a two level, not independent. These are a combination of the two different states. Okay, this is a symmetric and symmetric combination. Okay, now we'll jump into the Ravi formula. It's very important. In this concept, you need to understand first. Okay. So now we will look at the dynamics. Suppose assume it's a now we are considering a wave function, which is basically a linear superposition of two states. But now the basically if you consider the normalization thing, you will get key mod of CA star plus mod of CB star equal to 1, right? But it's no longer constant. This became a function of time. So this state will start evolve, right? It's no longer constant. So how the state will evolve? That will depend on this actual proportion. I mean the coefficient for the phi A and phi B, that is nothing but the CA and the CB ka value. Okay. Now, according to the Schrodinger equation, you know, I h cut is d psi dt equals to h psi d. Now, basically, if we consider this psi t and put it over here, and after simplifying, we'll end up getting something like that. Okay. So now assume at time t equals to 0, we are having this. Okay. But at time not equals to 0, so suppose, yeah. So by using the results in two part, we can get something like this, and psi naught will be this thing. So you can also take this thing as your homework. You can also put this thing, simply put this thing, and if you try calculating or further simplifying, you will end up getting something like this. So these are the some mathematical stuff. So in this way, basically, you can easily calculate what will be the your psi t. Okay. Yeah, that will be a function of time. So there is a lot of phase factor that you have to consider. So now the probability amplitude of finding the system at time t in the state. Let's say it will be psi. Let's say in the state. So what is the probability at a particular time? Because over the time it will change. Because now the C and CB no longer it's constant. It's became a function of time. So that's why at a particular time in the particular state of phi b particular probability, so combination of the phi b, as you know from the basic quantum mechanics, if you do the inner product you will get the probability. So then you have to just do the mod square of this thing. Then this you can see this like a sinusoidal thing, right? Sine square theta, there's a phase factor thing is coming also with the time dependent factor. Okay. If you simplify this equation 7 and 9, 7 and 9, you can get something like this. So this will be your probability. And another thing you can just, if I asked you to find the probability to find that to find this thing at a state of 5, you just need to subtract from the total probability, that is nothing but the 1. So now basically we define this root over delta square plus b square over h cut. as a Rabi frequency. This is nothing but the Rabi frequency. This is the important thing that you need to consider. So this is the probability of finding in this state. So this is it is a triangle function. Okay, the probability oscillates between phi and phi. So as you can see, if you look into this functional form, you will see it's basically oscillates. It's a there's sine square term. There's a sine square term, right? So that's why it's oscillating. But between 0 to v square plus v square plus delta square, it's a bounded between these two limit. So your amplitude is basically this, and p max will be 1 when delta is 0. Exactly. Of course, when delta is 0, p max will be 1. It represents the strong coupling. Obviously, if you go back to the old data series, you will see strong coupling means what? Strong coupling means delta will be very large. Exactly. And delta, if it is small, then delta is very small means it's a strong coupling. If delta is very big or V is small, uh, basically it's weak coupling. Okay. So the probability of to find the system in B is very small, right? So this is how the graph for PBA when coupling is very weak that you can see. You can look at the amplitude, right? What was here and what is there. So this is the concept behind the two-level system. Okay. Now I will discuss the residual resistivity of the metal. This portion I will discuss. Hello. If you have any questions, you can ask me anytime. So basically, the it's nothing but Rabi frequency is the frequency at which the probability amplitude of two atomic energy level fluctuate. Okay. So you it's a very important formula. Please mark this thing. One second. So I'm basically highlighting this portion. One second. So please remember this formula. It will help you to solve some problem. So this is called the Rabi frequency. Okay. This is root over delta square plus p square by h cut. Okay. So this delta, you know, It's coming from the energy difference, half of the energy difference between two states, and is the just you can call the mean of the two energy level. Okay. So this is the final expression. So its Rabi frequency is nothing but at which frequency the probability amplitude of two atomic energy level fluctuates in an oscillating electromagnetic field. Okay. So it is proportional to the, if you see the transition dipole moment of the two levels and the two to the amplitude of the electromagnetic field. Okay, not the intensity. It's proportional to the this exactly to the amplitude. So the population transfer between two levels, between the levels of such a two-level system, illuminated with a light exactly resonant with the difference in energy between the two levels, will occur at the Rabi frequency. When the incident light is detuned from the energy difference, then the population transfer occurs at the generalized Rabi frequency. Okay, so it's a kind of semi-classical concept, you can say, since it treats the atom as an object with quantized energy levels and the electromagnetic field as a continuous wave. Okay. Now I'll discuss another thing. So let's say it's an example. Consider this a system in which the time independent Hamiltonian possesses two eigenstate. Okay, so the same thing I have discussed, right? But it is in a simpler form. So if you calculate this thing, so just for the sake of simplicity, you can consider the diagonal elements of the interaction Hamiltonians are zero. Okay. So this is how it has been calculated. And also look into this example if you want. Okay, next I will tell you, I'll discuss the residual resistivity. Okay, 1 second. So in this question, it has been asked ki, why this residual resistivity of the metal comes into the system. So first option is it has been given ki, does it come because of the lattice vibration at high temperature, or second one is due to the phonon scattering at high temperature, third one is the temperature dependent, or is it temperature dependent or temperature independent. So to answer this question, we need to understand the concept. I mean, the understanding behind this thing. What do we exactly mean by the residual resistivity? So residual resistivity is an important phenomenon of the material that has been obtained at the absolute zero temperature. So generally, what we know. So, you, so at the zero temperature, we should ideally you should not have any kind of scattering processes, right? The system is completely in its ground state, but still it will have some resistivity. That is called the residual resistivity. So in metal, the residual resistivity, this arises some kind of impurity. Okay. So as we know, the system that we are dealing with, it's not exactly pure system. It will contain some amount of disorder, right? Some impurity disorder must be present in the system. So they will contribute at this zero temperature also. Okay. So if we don't consider the electron phonon scattering, electron scattering, if we not consider, but this impurity factor will be still there at the zero temperature, for which the residual resistivity arises. Okay, in the system. So residual resistivity of a metal is temperature independent. Uh, in the metal, and the collision of the electron with the impurity and the imperfect atoms happens due to the internal kinetic energy of the electron, not due to the temperature. Okay, so this is how it looks actually. So it's basically the residual resistivity of the metal at zero temperature. This is how it is changing, right? The total resistivity. Some constant factor is there, then it changes. Like it will be a power series. If you basically expand this thing, it will like rho naught plus rho t plus rho one rho one t plus rho two t square, like that, and so on. So this rho naught is called the residual resistivity of the metal at zero temperature. So that is why option 4 will be correct. It depends on the material. Okay. It doesn't depend on the temperature, but the total resistivity, it basically depends on the temperature. Then another thing, some of the questions was based on the. Let me check the time. You can ask me if you want to ask some questions. Anybody can stop me. Oh, thank God. Now it has come here. So, this is the superconducting coherence length. So this is the superconducting coherence length. So in superconductivity, the superconducting coherence length usually is denoted by xi, is the characteristic exponent of the radiation of the density of superconducting component. Okay, so please remind this formula because the superconducting coherence length is one of the two parameters of Ginzburg-Landau theory of superconductivity. It's given by root over h cut square by twice m of mod 2sm times mod of alpha, where alpha is the constant and the Ginzburg-Landau equation for psi. Okay, with the form of alpha naught T minus Tc. In the Landau-Mills theory, at temperature T near the superconducting critical temperature Tc. Okay, so psi T is basically psi T is proportional to the 1 minus T over Tc to the power minus half after a factor of root 2. It is equivalent to the characteristic exponent describing a recovery of the order parameter away from a perturbation in the theory of the second order phase transition. Okay. I'll put in presentation mode. In some special limiting cases, for example, in weak coupling BCS theory. So, 1 second. It's better if I just. So, what do you mean by the BCS theory? I'll tell you first this thing. There will be slight rearrangement in the slides. Yeah. So this BCS is called Barden, Cooper, and Cypher attributed the cause of the superconductivity, okay, to pair of electrons formed by the interaction between the two electrons. So that is also occurs via an exchange of a phonon. Okay, this is the theory. What BCS, all these three scientists has been predicted. So 1 second, I'll open my pointer. Yeah, so this is an electron phonon electron interaction. Three body interaction you can see electron phonon and again electron interaction, which is attractive and bind two electrons together forming a pair called Cooper pair. So it's basically a bound state which has been formed by the two electrons. Okay, this is called Cooper pair. So one electron interact with a positive ion in the lattice. So and deform the lattice, right? And the second electron with a compatible momentum passing nearby interacts uh, with the same ion in the disordered lattice so as to minimize its energy. As you can see, one momentum is k, and then after releasing the phonon, it's k minus q. It's simple. Again, it's interacting. It's becoming by as the direction has been changed, it's k prime. Then it becomes k prime plus q. Okay, then it's understood that. So let's say we have some cases. Let's say for weak coupling basis theory of isotropic case, there are a lot of AS type of superconductor, different type of superconductors are there that you can later also learn. You can also go through that if it is required. So it is related to the characteristic Cooper pair size. Okay, so it's defined by H cut VF by pi delta. Please remind this formula. It will be of great help. Okay, I'll just also highlight this thing. Okay, so this is the formula which is basically related to the characteristic Cooper pair size. Okay, so where as you know, H cut is the here the reduced Planck constant. M is the mass of the Cooper pair, which is basically just the twice of the electron mass because as two electrons are there, that is twice. And Vf is the Fermi velocity, and delta is basically the superconducting energy gap. Okay, so superconducting coherence length is just a measure of the size of the Cooper pair, the distance between two electrons. So if you are asked what is superconducting coherence length, you will simply say, so this is the distance between the two electrons, okay? And generally it comes of the order of 10 power minus 4 centimeter. So the electron near or at the Fermi surface moving through the lattice of a metal produces behind itself an attractive potential of range of the order of 3 times 10 power minus 6 centimeter. Okay, as the lattice distance of being a order of 10 power minus 8 centimeter, that you can compare the two length scale. Okay, the lattice length scale and the attractive potential range. Okay, so for a very authoritative explanation based on the physical intuition, see Søren this article. You can also go through this. Now I'll explain what is the London penetration depth in the superconductor. So there are some questions also there in the assignments associated with the London penetration length. So here I can just give you some examples formula, not more than that, because I cannot discuss, because I'm not supposed to discuss all the questions what was given in the assignments. So this is very simple. If you just simply go through it. Uh, 1 second. Let me check once. Yeah, we have time. So let's say one of the theoretical approaches to the description of the superconducting state is the London equation. Okay, so it relates to the current of the current density to the magnetic field as it is shown here. So So as you can see, the London penetration is basically depth is the distance required to fall the magnetic field and intensity 1 over E times the externally applied field B. So this length basically once this applied field inside the superconductor becomes 1 over E times of the applied field. So that, I mean, the required distance, I mean, within that distance, if it is happening, that distance is called the London penetration depth. So by definition, B inside will be equal to the B applied times E power minus X by lambda L. This lambda L is your London penetration. 1 second. London penetration depth. Okay. So there is a comparison. I mean, there is a table that has been prepared for different materials. If you wish, you can go through it and save this thing. So for this, these are the different kind of materials are there. For all these different materials, we have listed the coherence length and the London penetration length. So you'll have an idea of how the ratio of the London penetration length with the coherence length. See, for the aluminum, coherence length is very high compared to the other existing metal. So, and also you can see the London penetration depth for all the materials. So the London equation can be shown to require that the magnetic field is exponentially decays to zero inside a superconductor. This is a basically imaginary effect. I think I'll also discuss that thing. So the nature of the decay depends upon the superconducting electron density. Okay, so you can simply also please remind this formula. Okay, it will also help you to solve some problems in future. So how the London penetration depth is basically related to the superconducting electron density. Okay, so basically lambda L equals to root over epsilon naught mc squared by n squared. Okay, so as I've already told what is coherence length. So one of the coherence length for the description of superconductor is called the coherence length. Okay, it's related to the Fermi velocity, of course, for the material and the energy gap of the superconductor. I mean, which is associated with the condensation of the superconducting state. It has to do with, in fact, the fact that that superconducting electron density cannot change quickly. So there is a minimum length over which a given charge can be made. So this it destroys the superconducting state. For example, the a transition from the superconducting state to a normal state, like metallic state, insulating state. This is the called the normal state. We'll have a transition layer of finite thickness, which is related to the coherence length. So how these are related? Basically to the Fermi velocity and the superconducting band gap. So this is the formula. So this is how the coherence length is related to your Fermi velocity and the superconducting band gap. So see, this London penetration depth refers to the exponentially, as I already mentioned, it refers to the exponentially decaying magnetic field at the interior surface of a superconductor. It's also related to the density of the superconducting electron in the material. The fact of exclusion magnetic field from the interior of the superconductor, that is basically called the Meissner effect. So now we'll see the Meissner effect from the London equation. Okay. So as you know, the London equation relates the curl of the current density to the magnetic field. Okay. So this is the curl of J is equals to minus 1 mu naught by lambda L square times B. So if we relate by relating the London equation to the Maxwell's equation, so by Maxwell equation, what we know? The curl of B is basically mu naught J. J is the current density, right? So to do this thing, we have to again take the curl, right? Because see here from the London equation, we know the curl of J. This is how it is related with the magnetic field. But from the Maxwell's equation, how J is related to magnetic field, this can be described by this equation. But to compare this thing, we need to take the curl on both the sides so that we can get the curl of J thing, so that we can convert this thing to the magnetic field. That's why after taking the curl on both the sides, what we have, so curl of curl, that is equals to curl of mu naught J, which is equals to minus B lambda L square, right? So this is curl square B equals to B by lambda L square. So since grad square B equals to 0, by Maxwell's equation, the value for V inside the superconductor must be identically 0 unless the penetration depth is infinite, right? So that is not possible. So that is not a superconductor, right? So this is one of the theoretical approaches by to explain the Meissner effect. This is the same thing as been shown, how the B is basically decaying inside the superconductor exponentially. So this is related to the superconducting density. So this estimate, I mean, the order of the magnitude is very important. Whatever I have discussed, I mean, told, it's very important to relate the order of the magnitude to get a feel or sense ki how it is. So there are also some questions on Andreev reflection. So we need to understand what is Andreev reflection first. So Andreev reflection, one second. If you have any doubt, you can ask me. Otherwise, it will be difficult. Second. So, anti-reflection is a type of particle scattering which occurs at the interface between a superconductor or a normal state. That you can see, if you consider this side to be normal, this is the superconductor side. Okay, it's a basically charge transfer process by which a normal current in N is converted to a supercurrent in S. So this side it was normal, but here it will get converted after the transferring of the charge. It will convert into the supercurrent. Each anti-reflection transferred a charge of twice across the interface. That is obvious, right? If it is transferring one more electron here, so one, so two electron charge 2e across the interface, avoiding the forbidden single particle transmission within the superconducting energy gap. So you can see an electron, it has been denoted by red color. This, okay. So meeting at the interface between a normal conductor and a superconductor produces a Cooper pair in the superconductor and a retroreflected hole in a normal conductor, right? So it's basically the spin conservation and the conservation of spin and conservation of the charge, right? That is why a hole is basically generated in the normal conductor, and so in the superconductor region, a Cooper pair has been formed. This is the Andrew reflection. So now we'll discuss the superconducting tunnel junction. Okay, so it's superconducting tunnel junction, also known as the superconductor insulator superconductor tunnel junction (SIS). It's an electronic device which is basically consisting two superconductor, but these are separated by a very thin insulating material. So current passes through the so current passes. 1 second. So current passes through the junction via the process of quantum tunneling. Right. As you're, I hope you are aware of this quantum tunneling. So it's basically a when you have a barrier, electrons tunnel through that barrier. If that barrier has some kind of potential profile, right? And also depending upon the potential profile, the electron will have a certain probability to tunnel through the barrier from one side to another side across the junction. So this is the quantum tunneling phenomena, right? So this STJ is a type of Josephson junction. So that's what I will also discuss in the next slide. What do you exactly mean by the Josephson junction? So though not all the properties of the STJ are described by the Josephson effect. Okay. So all the currents flowing through the STJ pass through the insulating layer via the process of quantum tunneling, as I've already mentioned. So these are the two components of the tunneling current. First, from the tunneling of Cooper pairs. So it's a bound state that I've already mentioned, bound state of two electrons. And this is the flow of the Cooper pairs is basically considered as a supercurrent. So this supercurrent is described by the AC and DC Josephson relation that I'll show you later. So for this the first one is this. Okay, the ton is coming from the tunneling of the copper pairs. The second one is the quasi-particle current. What is the which is in the limit of zero temperature? It arises when the energy from the bias EV exceeds the twice value of the superconducting energy gap. Please mark this statement. It will help you to solve the questions. So this is the concepts are very important here. So I'll mark. So this second is the quasi-particle current. Okay, in the limit of zero temperature arises when the energy from the bias, because we are applying some bias, right? Apply EV exceeds twice the value of the superconducting energy gap. Okay, please note it down. It is very important concept. Now at finite temperature, a small quasi-particle tunneling current, it's called the sub-gap current. Okay, it's present even for voltages less than twice the energy gap due to the thermal promotion of the quasi-particle above the gap. Okay, so this is the schematic. So the illustration of a thin superconducting tunnel junction. So superconducting material is basically the light blue. It's mentioned in that way. It's been described in that way, and the insulating barrier is the black one. It's very thin layer. You can see the substrate is green. So suppose this junction is irradiated with photon frequency F, then the DC current voltage will exhibit both the Shapiro state that I'll show you. What does it mean by Shapiro state? So if you carefully look at into the IV characteristics of that, I hope you have already our instructor has been instructor has discussed this thing. So it means K Shapiro step is like this. Okay. So in the IV characteristics, so this side is V. It will be like step like. That is why it's called Shapiro. Okay. Shapiro steps arises from the the current voltage curve will exhibit both the Shapiro steps and also steps due to the phonon assisted tunneling, right? Because of the quasi particle. So this, let me change it to the laser pointer. So Shapiro step arises from the response of the supercurrent and occur at the voltage equal to NHF by 2IC. This is very important. So at a particular voltage value, it will be equal, and phonon assisted tunneling arises from the response of quasi particle and gives rise to the step displaced in the voltage by NHF by E relative to the gap voltage. Okay. So this is the typical energy diagram of this SIS, superconducting insulator, superconducting junction, tunnel junction. So the vertical axis is basically your energy, and the horizontal axis shows the density of states. So Cooper pair exists at the Fermi energy indicated by the dashed line. A bias voltage is applied across the junction, the shifting the Fermi energy of the two superconductor relative to each other by an energy EV, where is the electronic charge, right? So this quasi-vertical states for the energy greater than delta from the Fermi energy, where delta is the superconducting energy gap. I mean, quasi-vertical state will only exist that I've mentioned when the energy is greater than the this delta from the Fermi energy, right? But delta is the superconducting energy gap that I've already mentioned. So this green and blue indicates basically empty and filled quasi-vertical states, respectively, at the zero temperature. So as I've mentioned, you will get to see the Sapiro steps. I mean the how it will change. I mean when the current, the critical current will take a finite value. So this is the sketch of the current voltage curve of a superconducting tunnel junction. So when exactly the Cooper pair will start tunneling, will have the critical current. So the Cooper pair tunneling current is seen at V equals to zero, while quasi-vertical tunneling current is seen for V when it's on the right hand side. V is greater than 2 delta by E and less than minus 2 delta by E. Okay. So this is the typical device schematic. I mean how it has been built. So these are two. uh, Josephson is called the Josephson equation. These two are the. Okay. These two are very important. How the, I mean, see, when this electron, this side of the superconductor, so this is why it's called the macroscopic phenomena. This is the beauty of the Josephson junction. So you can describe the whole superconductor as a single phi phase. I mean, this phi is coming from the microscopic origin, but still you can consider they define the whole superconductor by a single phase. So that's the beauty of this Cooper pair formation. I'll tell you on this side, when we are having the phase difference, only then we'll have the supercurrent in the right. Otherwise, if phi is zero, the supercurrent is zero. So that is why it's important to have the phase difference when the, I mean, two Cooper pair can tunnel, right? So this IT is basically IC sine phi t. It's like oscillates sinusoidally. So this can be a function of time. This phase when you have applying a potential. If V is zero, no radio frequency or nothing you are applying excitation, then the phi will stay as constant. If you are applying some potential, then phi will evolve over the time. That is why here V and I are the voltage across and the current through the Josephson junction, and IC is the parameter. It's called the critical current. Is the parameter of the junction. Okay. So equation one is called the fast Josephson junction or weakly current phase relation. The whatever we have placed in the middle, that's called the link. I mean link between two superconductors. Okay. Here insulator is the link. And equation 2 is called the second Josephson junction or superconducting phase evolution equation. Okay, that's what I mean we understood. So the next is, sorry, the critical current of the Josephson junction depends on the properties of superconductor and can also be affected by the environmental factors like temperature, externally applied magnetic field, and so on. Yeah. Hello. Hello, there is some connection issue, I think. Sorry. Yeah. So, uh, Josephson actually made a remarkable prediction that is a zero voltage supercurrent, right? So, this is the scenario when I have told ki if the we don't have a, let's say any voltage we are applying, then what will happen? Del phi del t will become zero, then phase will become constant, right? So once the phase is constant, so I simply equals to IC sine del phi. Del phi is not a function of time then, right? So the zero voltage supercurrent IS should flow between two superconducting electrodes separated by a thin insulating barrier, right? So here, del phi is the difference in the phase of the Ginzburg-Landau wave function with the two electrodes, and the critical current IC is the maximum supercurrent that the junction can support, right? We further predicted that if a voltage V were maintained across the junction, that's what I've already told you. Okay, this phi would evolve accordingly. That is the second Josephson current, right? Now, this is the important part. So, the current would be the alternating current of the amplitude IC, and the frequency will be how much? The frequency will be 2 EV by H. So this will be the oscillating frequency of the current. So thus the quantum energy H nu equals to the energy change of the Cooper pair transferred across the junction. So this predicted effects known as the DC and the AC effect respectively. So these are the you already have known the DC Josephson effect and the AC Josephson effect. So different we can have a different scenario, right? So for the junction, so that's how the phi del phi will evolve or del phi will change. So we can have a oxide barrier, right? So first one is the insulator. We can have a insulator that is placed between the two superconductor. That is called this is the different kind of Josephson junction that will be called SIS. Now, if we put a normal weakly superconducting proximity layer, this is a very weakly coupled. Okay, these two states, the superconductor one and two, then it will be called SNS. Now, if it's very there is a constriction between two superconducting electrodes. It's called it will be called SCS. Okay, that is called the superconducting SCS. So there are three types: SIS, SNS, and SCS. Also, there are recent study that has been also they a few scientists has been indicated key we can also just finding a carrier density of the material just by introducing a material called twisted bilayer magic angle twisted bilayer graphene. If we simply place this magic angle twisted bilayer graphene in between two superconductor, I mean the layer, we basically, as you know from the property, it's a advanced research that is still going on, that has been already paper has been published. So just by changing the carrier concentration, you can get a superconducting state, insulating state in this material. That's the beauty of this magic angle twisted bilayer graphene. That is why it's called magic. Okay, so simply using the same material as tuning your gate or the charge density, you can make this kind of Josephson junction. Also, you will observe the DC and AC Josephson effects. This is just for the information sake I'm telling you. So this is the basic idea behind the Josephson junction. Okay. So with this, I would like to end today's session. So I hope this will be helpful. Though I will also share the all the slides for this. And you can. I think if you go through this, go through the all the slides and this video, you'll be able to solve all the questions. This is very basic. So you can also send me an email or contact me if you want regarding any questions or anything. So I'll meet you on next Saturday then for the next tutorial session. Okay, bye.